let's take a look at these orbitals, what they look like. I have some 2p orbitals. There are 3 of them. Okay? These p orbitals will always come in sort of groups of 3, and they're all the same. The only difference is their orientation. So we can imagine each of those p orbitals being aligned with a certain axis in the three-dimensional coordinate system. Right? So a 2px orbital has its 2 lobes sitting along the x-axis. It turns out the node is along the y and the z plane. Okay? So there's a lobe on the right-hand side of the x-axis and the left-hand side of the x-axis, and there's a plane that goes through them that defines that node. So 2py goes along the y-axis, 2pz goes along the z-axis. So those 3 orbitals, they're actually superimposed on top of each other. So if we go to my 3D molecules, my very first model here, first of all, it's atomic orbitals. We'll get to hybrid orbitals in a minute. But 2s is just a sphere. Okay? That means there's 2 electrons that can exist within that sphere. And then here's 2px. 2 lobes along the x-axis. 2py. 2 lobes along the y-axis. And 2pz. 2 lobes along the z-axis. So we have 6 lobes altogether, but the lobes really don't mean too much. It's the orbitals themselves. So please don't confuse yourself by thinking there's 1 electron in each lobe. It's not really how it works. There's 2 electrons if I just show one of these orbitals. Here's 2px. Okay? There's 2 lobes right there. Okay? The 2 electrons in that orbital can exist anywhere within those 2 lobes. So try to break yourself of always trying to imagine where an actual electron is, and try to just think of it more as that this entire orbital itself will house 2 electrons somewhere within there. Okay? And those actual 2 electrons are just behaving as these lobes in this 2p orbital. So let's talk about how it is that electrons will actually fill into available orbitals. There are 3 principles that define how it is that electrons will fill into available orbitals. So first is the Aufbau principle, that electrons fill in lowest energy orbitals first. So 1s, just like we showed before, is the lowest energy orbital, and that's just the first shell. All it is that 1s orbital. Then we have 2 electrons that go into the 2s orbital, another spherical orbital that's just larger than 1s. Electrons will fill into the 2p orbitals. There are 3 of those 2p orbitals, and we'll talk about how it goes into each of those, but 3s is next, 3p is next, 4s, and then 3d. And this is always a huge point of confusion for a lot of students, and the way that I can best describe that is that the 3rd shell gets divided into these subshells. So one is an S, some of them are P's, some are D's. Right? The S's are always lower in energy than the P's, and those are always lower in energy than the D's. But it turns out that in the next shell, the 4s subshell has split off and has become so much lower in energy that it actually has overlapped the 3rd shell. So if you just sort of think of it that way, that the 3rd shell has spread out into those 3, the 4th shell has spread out into its subshells, but the lowest energy orbital of the 4th shell actually is lower in energy than 3d. So when it comes to filling in these electrons with the periodic table even, well, you'll be able to see that these S sections correspond to the left 2 columns on the periodic table of the main group. The P sections correspond with the right-hand side of the main group. And then D only happens when we're filling in transition elements. So we can actually write that here, 3D. We're only when we get to transition elements do we start with 3Ds. So that's the Aufbau principle. The Pauli exclusion principle is that electrons will have an up or a down spin. Okay? And spin is another sort of weird quantum mechanical thing. One way to visualize it would be thinking of electrons that are spinning around like a top. Okay? And they can either spin one way or they can spin another way. Now, that's not actually what's happening. It's actually a little more complicated than that, but it's a decent way to visualize it. You can pretend that that's what's happening. It's all it is that there's just something fundamentally different between the two electrons that will occupy one orbital. And one of them has what we call an up spin and one has a down spin. So we just indicate that with an up arrow and a down arrow. So that is just a requirement in order for those two electrons to be distinct from each other. Okay? Pauli exclusion principle just tells us that it's impossible for us to have two identical electrons in an atom. And if I had two up-spin electrons within the same orbital, there would be nothing distinct about those. So one has to be up and one has to be down. So the last principle is Hund's rule. If there are equal energy orbitals, electrons fill one per orbital first before they pair. So remember, there are three of those 2p orbitals, right? 2px, 2py, and 2pz. So I can fill up to 6 electrons in this entire set of 2p orbitals, but if I only have 3 electrons to put in, I'm going to start with one of them in 2px, the next one in 2py, and the third one in 2pz. They like to spread themselves out like that because electrons repel each other. It would be unfavorable for 2 of them to pair up in 2px first because they'd be too close together. They'd much rather spread out in space over those 3 orbitals. And only then, if we need to add a 4th one in, that would go in 2px with an opposite spin. So they start out with parallel spins first. So I just sort of by convention drew 3 up first, and then the 4th one went down. The 5th one would go down, the 6th one would go down, filling those ones in that way. Right? So let's just do a little practice with writing electron configurations based on those 3 principles. So hydrogen, very first element on the periodic table, hydrogen just has 1 electron. So let's do the Aufbau principle. We start with just the very lowest energy orbital available. So 1s is where that 1 electron will go. And to make an electron configuration, we say 1s 1, where that superscript number is how many electrons can be described by that designation. Okay? So just a single electron in 1s. Another way to draw that is to show some levels. Let's start with 1s down low and just draw a single up arrow next to it. That just shows 1 electron that's in 1s. Nitrogen, let's take a look at our periodic table. I had one a couple of pages ago. Just to refer you to nitrogen so you know where we're going. If I count up how many electrons had to go into nitrogen, nitrogen has an atomic number of 1, 2, 3, 4, 5, 6, 7. Okay? It's 1 past carbon, right? Carbon was 6. So nitrogen has to have 7 electrons within it. So I'm going to fill in 1s. Let's start with 1s. And remember, every orbital can hold 2 electrons, so 1s2. Okay. Next came 2s, so 2s2. That gives us 4, which means 2p will have to hold 3. That gets us up to 7. And so why is it that 2p can hold more than 2? Well, let's draw our little diagram to remind ourselves. 1s is just a single orbital that holds 2 electrons. 2s, again, single orbital, 2 electrons. 2p, though, has 3 orbitals that can hold up to 6 electrons. Remember how we do this? I have 3 equal orbitals, 3 electrons. I'm going to put the first one in the first orbital. Where's the second one going to go? I'm not going to pair them up because they want to spread out. I'll do like that, 1 in each of the 2p orbitals. Right? So you can, on your own, go through carbon, oxygen, and fluorine. In the completed notes that I'll post after this, you can check your work with those.